All right, so let's take a look at section 5.5. Okay, it's called the dot product. So we've talked about how to add vectors. We've done it visually, and we've done it just with numbers. Subtraction, we did it visually and with numbers. We did multiplication, but as a scalar. So basically, we took a number times a vector, okay, which can make it longer, shorter, or flip the direction. Well, the dot product is a way we can multiply two vectors together. Okay, it's not the only way. It's one of two ways that are in our book. So if somebody said to you, I want you to multiply these two vectors together, you'd have to ask them how. Do you want me to do a dot product, which is what we're going to learn, or do you want me to do a cross product? We're not going to be getting to cross product. Okay, part of the reason for that is cross products can only be done in 3 dimensions. We haven't even studied much about or anything about 3D yet, so we won't be doing cross product. Okay, so suppose we have two vectors, v and w. All the coefficients there would be numbers, like 3i plus 2j and negative 6i minus 7j, or something like that. Okay, I'm going to give you the formula for how you find the dot product. It's very simple. Find the dot product. You take the two numbers in front of I for each vector, multiply them together. Take the two numbers in front of j for each vector, multiply them together, and then add those two answers up. Okay, that's how you find a dot product. So multiply the x components plus multiply the y components. So we said earlier, A1's a number, A2's a number, B1's a number, B2's a number. What do you get if you multiply a number times a number? Another number. Right? You get another number. So when you do an A1 times A2, you get a number. B1 times B2, that's a number. And then you're going to add two numbers together. What will that give you? Another number. So the point here is when you do a dot product, the answer is a number. Okay? It's a number. Not a vector. It's not a vector. So I can say answer is a number. Right, let's see if we can find the dot product here. So we have v is 2i minus 3j, and w is 5i plus 3j. Hey, Sean, can you tell me what my first two numbers I'm going to multiply together are?
2 and 3.
Well, what's my number in front of I for the first vector? 2. What's my number in front of I for the second vector? 5. Those are the numbers you multiply. So good. 2 times 5 plus, how about Ashley? What are the other two numbers I'll multiply?
Negative 3 and 3.
Yep, I'm going to multiply negative 3 and 3. So we do 2 times 5 is 10. Negative 3 times positive 3, that's a negative 9. And Olivia, if I add those up, what's 10 plus negative 9? 1. And that's the answer. That's the dot product. 1. Well, we're going to do a little bit more with the dot product, but yeah, not just that. Any questions on how we found that? And the way you pronounce this, in case I didn't mention, it's v dot w. You can't say times, because if you say times, somebody would ask you, do you mean dot product or cross product? So if you're doing a cross product, it looks like this. Pronounce that v cross w. This is v dot w. Okay? So that way there's no confusion. Let's switch it. Let's find w dot v. Okay. Anybody tell me, how's that going to change that first part? It's not going to be 2 times 5. It's going to become 5 times 2. And the second part?
3 times negative 3.
3 times negative 3. All right, so now you're starting with W. So we had the 5, and then the 2. And we had 3 times negative 3. What do we end up getting, though? We still end up getting 1. This time it's 10 plus negative 9. It's exactly the same thing. So what does that mean? If v dot w and w dot v come out the same. Yep, they are equal, and there's a word for that. When you can switch the order, you multiply two things in. Anyone remember that word? It's not associative. That's commutative. Okay, commutative. So the dot product is commutative. Well, you might say, well, isn't that just always true? Anytime you multiply two things together, you can switch the order and it comes out the same? No. If you were to do a cross product, v cross w and w cross v, they come out opposites. So it's different. Okay. We don't have to worry about that one. All right, let's find v dot v. Okay, so you're going to take a vector and dot it with itself. Okay, so let's just copy v down so we can see it. It's 2i minus 3j. Okay, anyone can tell me what's the first part of the calculation going to look like here? Yep, it's going to be 2 times 2. Plus negative 3 times negative 3. Good. And Ben, what does that come out to? 13. We get 13. Anybody see a connection with that number and the vector v? It's not quite this thing, but it's close to it. If not, we'll do w dot w and see if you see it there. But anybody see what the 13 and the vector v? This kind of describes something about it. Almost. Not quite.
It's almost like the magnitude.
Yeah, if you put a square root on it, it would be the magnitude. Remember how you find the magnitude? Take the 2 and square it. Take the negative 3 and square it. Add them up. But there's one more step if you're finding the magnitude. You take the square root. So this number is what would be under the square root. Right? The 13. Let's try w dot w. Okay, so what was w again? That was 5i plus 3j. Okay, so Adam, what's going to come first?
5 times 5.
Yep, 5 times 5. And what's going to come second?
3
3 times
times 3.
3. So I get 25. Plus 9, which gives me how much? 34. And again, if you're going to find the magnitude of w, it'd be 5 squared plus 3 squared. That's 34, but then you'd be taking the square root. Right? So dotting a vector with itself is almost like finding the length, except you leave off the square root part. Any question on that? So this is what we just said. If you dot a vector with itself, you don't get the magnitude of the vector, because the square root's not there. You're getting the magnitude squared. So dotting a vector with itself, it almost gives you the magnitude, but you're missing the square root. That's why it's squared. And then if you did take the square root of each side, square root and square would cancel. And the square root of the dot product, that would be the magnitude. Just have to add in the square root. Okay, let's see what happens when we dot a vector with 0. Okay, Tom, can you tell me the first part of my calculation?
2 times 0.
Yep, 2 times 0. Okay, Brandon, the second part?
6 times 0.
Yep, 6 times 0. And Yadira, what's that going to give me?
8.
So what's 2 times 0?
0.
0. And then 6 times 0 is 0. And then 0 plus 0? Yeah, 0. Now the question is that 0 the number? Or should I put an arrow and make it 0 the vector? Why is it going to be a number?
Because v times w is a number.
Right, when you find a dot product, the answer is always a number, not a vector. Okay, so if I had a kind of a tricky problem on a test would be if I put that as an answer, and I put that as an answer. This is wrong. It's not a vector, it's a number. Okay. Any question on that? All right. So with the dot product, you can do the distributive property. Okay, it does work. We know the distributive property works for regular multiplication. If you do that out, that's fine. But the dot product, that's a different kind of product. But it does work. So you can do u dot v, the plus, and then u dot w. So you can apply the distributive property with dot product. All right, another thing that the dot product allows us to do is figure out the angle between two vectors. Let's say you had a vector like that and a vector like that. One way we could figure out this angle is we could go back to law of sines and cosines. If you know the length of this side and the length of that side, you could find the length of that third side very easily. Just use your distance formula, find the distance between 2 points, and you basically have a triangle. Side, side, side. Right? And you could find any angle you want with law of cosines. But there's a better way. Okay? Instead of having to go back to law of cosines, okay, you can use this formula. Okay, the formula, it's on page 347. The proof of the formula is generally something I do in pre-calculus, but I'm going to hold off on doing it. I'm not going to be testing you on the proof. I'm just going to test you on how to use the formula. But the proof actually uses the law of cosines. That's how you do it. Okay, so if you want to find an angle between two vectors, you need to know three things. The dot product, the length of u, and the length of v. And you plug them into that formula. And what would be your last step? Because eventually you're not going to want to have the cosine of your angle. You want just your angle. So how would you get rid of the word cosine? Yeah, you're going to end up doing inverse cosine. Okay, it's one of your last steps. Okay, so in case you aren't sure what the denominator means, that's the length of u times the length of v. Right, so let's find the angle between u and v. Okay, let me sketch it roughly so you can kind of get an idea of what we're finding. So we got a vector that goes right 4 and down 3. So something kind of like that. Then we've got one that goes right 2 and up 5. So what we're finding is this angle right in there. Let's start with our dot product. Josh, can you tell me what I'm going to multiply together to find the dot product?
4 and 2 and 3 and 5. Or negative 3 and 5.
So, yep, 4 and 2. And negative 3 and 5. Okay, so 4 times 2, Sarah, that gives me 8. Negative 3 times 5 is negative 15. And 8 take away 15, Tom, will give me, yep, negative 7. Good. Okay, so that's going to be your numerator. In your formula, that's going to go in the top. Now, 2 more things. Let's find the length of u and the length of v. Okay, always start out with your square root. And Sam, how do I get the length of u?
4 squared.
Yep. So I'll do that out. So 4 squared. And then what comes after that?
3 squared.
Okay, negative
Negative 3 squared.
3 squared. Well, I'll do it in 2 steps then. What goes between them? Plus sign, good. So now we're going to get 16 plus 9. So that's the square root of 25, or how long is u? 5 units. Good. Nice. Any question on how we got the length of u? Let's do the same thing and find the length of v. And then once we have all 3, we just put them in the calculator, and we'll have our answer. Max, can you tell me how I'm going to get the length of v? So for v, we have a 2 and a 5.
What's that, 2 squared?
Yep. 2 squared
Plus 5 squared.
plus 5 squared. Let's see what we got. 2 squared is 4. 5 squared is 25. So that gives me the square root of 29. Don't bother rounding it off. We're just going to plug it into the formula. Okay, Ben, what trig formula does that, or what trig function do we use here to find the angle?
Sine.
Not sine. What did we have up above it in the formula?
Cosine?
Yeah, we had cosine, right? Cosine
Oh, right, yeah.
theta. So theta, that's your angle. Okay, you're trying to find theta. The cosine of your angle is equal to the dot product. That goes on top, divided by the product of the magnitudes. Magnitude u, magnitude v. Okay, earlier we mentioned our last step here to get theta by itself. We get rid of cosine. How do we get rid of cosine? Yeah, inverse. Remember, cosine is a function. You can only use division if you have numbers, okay, or letters. But with a function, you got to use another function. So take the inverse cosine of what's on the left. Do what's on the right, and now plug that in. Whatever that comes out to, that's your answer. Okay, you can do it. You can do it in degrees or radians. I'd say let's stick with radian degrees for this problem. So second inverse cosine of -7. Now, if you're going to type it all in at once, just be careful with your order of operations. So I'll do 5 square root 29, and put that in parentheses. It'll do that denominator first, and then -7 divided by that denominator. So I get an angle of 105.09. And from my sketch, that was just a quick sketch, but that looks reasonable, about 105 degrees. Any question on that? It's finding the angle between two vectors. So sometimes when you have the two vectors, there's a certain angle between them that makes it special. And one special name we have is if the vectors are perpendicular, means the angle between them is 90 degrees. But when we talk about vectors, we use the word orthogonal. You could say the vectors are perpendicular, but generally they use the word orthogonal when we talk about vectors. And figuring out if vectors are orthogonal is actually pretty easy. Okay, it's kind of a shortcut. What did I say a second ago? If they're perpendicular or orthogonal, what's the angle between them? 90. Okay, so let's look at our formula. Let's fill in 90 for cosine and see what happens. So we have cosine of 90. And you'd have your fraction on the other side, whatever that is. But let's take the cosine of 90 and see what we get. 0. Maybe we get 0. So if they're orthogonal, cosine of 90 is 0. And you have your fraction on the other side. What's the only way that a fraction could ever equal 0? Only if the top is 0. The top has to be 0. It doesn't matter what's in the bottom. You don't even need to figure out what's in the bottom. The top has to be 0. Let's go back and look at our formula. What's in the top of that fraction on the right-hand side? And what is that called? How do you say that again?
Dot product.
That's the dot product. So if the two vectors are going to be perpendicular, all you have to check is the dot product. If the dot product comes out to 0, you're done. Okay? So that's a shortcut for perpendicular. If two vectors are perpendicular, their dot product is 0. Okay, so it's kind of a nice shortcut. Okay, so example 4, just a yes, no. Are these vectors perpendicular?
No.
No, they're not perpendicular. If you find the dot product, what number is in front of I and j if it's not written?
1.
It's a 1. So think of it as 2 times 1 plus 1 times 2. If your numerator is a 4, that's not a 0. Had to be a 0 if they're going to come out perpendicular. Anybody see what you could do to that? What could you change here? There's actually a lot of things you could change to make it somehow come out to 0. You just add in one small thing. Yeah, you could put a negative sign in somewhere. Actually, it doesn't matter where. Put a negative on any 4 of those. Just one at a time, though. Pick one and make it negative, and then they would be perpendicular. Okay, so you put it on the 2 here. Now you've got negative 2 times 1, positive 2 times 1. Now it would come out to 0. Okay, so the answer was no. Right, now parallel. Okay, if vectors are parallel, there's 2 cases. There's an example of parallel vectors. The angle between them is 0. Okay, the angle between them is 0. How can you tell? If you line them up, they're right on top of each other and they point the same way. There's a 0 degree angle between them. Okay, the other way you could have parallel vectors is if you had this. Well, mine wasn't perfect, but those would also be parallel if they point in opposite directions. Like that. Those two vectors would never cross because they're going opposite directions. So if you've got two vectors, they could be parallel if the angle between them is 0 or 180. Let's plug that into our formula and see if there's a shortcut for that. So remember, cosine, angle, and we've got our fraction. Let's take the cosine of 0. So cosine of 0 comes out to 1. So how could that happen? What's the only way that a fraction could ever come out to 1? And this is how you're going to know if they're parallel. Yeah?
If the numerator and the denominator are the same.
Great. Your numerator and your denominator have to come out the same. It's one way. Okay? The dot product and the product of the magnitudes comes out to exactly the same number. If that happens, you're going to get a 1. And that means they're parallel. Let's look at 180. Let's look at the other angle. Let's plug in 180. Take the cosine. This time we get a -1. Okay, this is the other way they could be parallel. When would a fraction come out to -1? Yeah, if you're dividing two numbers that are the same, except one of them has a negative. So the short version here is if your numerator and denominator come out the same or they come out opposites, then you know they're parallel. So parallel is a little more work. You still got to find the denominator. You can't just ignore it like perpendicular. Right, so very similar to example 4, just determine if the vectors are parallel. Right, so let's find all three things. Let's find the dot product, the length of V, and then the length of W. Okay, Emily, what's going to be the first two things I multiply to get the dot product? 4 and 20. Good. Okay, how about Michaela? Next two things? Okay, -5 and -25. So multiply 4 times 20, that gives me 80. -5 times -25, well, cancel the negatives out. And what's 5 times 25? 125. Okay, add that together. What's 80 plus 125? How much? 205. Okay, so there's our dot product. Okay, length of V, 16 plus 25. Add them up and take the square root. Just leave it as the square root of 41 for now. Okay, let's check W. 400 plus 25 squared. It's going to be 625. Square root of 20. 625, add them up. That's 1,025. Now, neither one of those numbers have very nice square roots. That's the square root of 1,025. That's the square root of 41. Okay. So I can't tell yet when I multiply those together if it comes out to 205. So I'm going to use my calculator. So I'm going to set this up like I have no idea if they're parallel or perpendicular. I'm going to assume it's an angle that's neither. Maybe it's 93.5 or something. Yeah? So put your dot product in the top. square root 41 times the square root 1025. Let's see what the denominator comes out to. What am I hoping it comes out to if they're parallel? 205 or negative 205. Okay, one of those two. So take your square root of 41 times square root 1025. 205. So we ended up with 1. Okay. What does that mean? If we end up with 1 there, parallel. Yeah. They are parallel. Right, so there's no need to check anything else. If it comes out 1 or negative 1, they're parallel. Okay. Any question on how you find the angle between two vectors or determine if they're perpendicular or parallel? All right. This will be our last example. Okay, this example is going to take a little bit of what we did yesterday about velocity vectors. We're going to use those. And we're going to try to figure out what's happening to an airplane. Does everyone understand the difference between airspeed and ground speed for an airplane? The difference is? You don't think they could explain it, what that means? No? Okay. Well, airspeed is the speed of the plane that if the pilot looks at his, I don't know if they call it a speedometer in a plane, but if he looks at the speedometer, it's how fast the wind is moving over his plane, right? Ground speed is the speed, if you look at the plane from the ground, how fast does it look like it's moving? Like if you had a radar gun and you could point it at the plane and get the speed, that's the ground speed. And they're not always the same. Imagine a plane that's flying into a wind that's 200 miles an hour. Right? Let's say if the plane was, normally if the plane was going 300, but it's flying against a wind that's 200, how fast would it look like the plane is really going? It would only look like the plane is going 100 miles an hour from the ground. The instruments on the plane would say 300, but that's because the wind is blowing against it at 200. Okay? So there's a difference between the airspeed and the ground speed. That's the difference. So this airplane is maintaining an airspeed of 500 miles an hour, and it's going directly south. South is straight down. Okay? The plane is flying in a jet stream. The jet stream is 80 miles per hour, and it's blowing exactly north and east. So that's going to make the angle easier to figure out. It's 80 miles per hour blowing northeast. So what I want to do is find out what the actual speed of the plane is. Okay, let's sketch it. First of all, let's see if the wind is helping the plane or is it hurting the plane. Okay, sometimes if you have a tailwind, that's good. Tailwind blows the plane in the direction it's trying to go. Headwind, it's fighting it. Okay, so it's going to slow the plane down. All right, so let's draw the speed of the plane. So that's 500 miles per hour south. What's a perfect way to represent a speed and a direction on a graph? What can I use? Well, I want to represent a magnitude and a direction at the same time. A vector. Okay, I'm going to draw a vector for the plane. Okay, so what I'll do is have this, again, it's not to scale, but just represent the plane. And well, let's make it red and a little thicker. Okay, so that represents the speed of the plane, 500 miles per hour south. Okay, Now, the wind, that's 80 miles per hour, so it's not as long of an arrow, a little bit shorter, and it's blowing northeast. Which quadrant would be northeast here? Quadrant what? 1. Yeah, it'd be quadrant 1. This is north, east, west, and south. Okay, so let's draw in a vector for the wind. Okay, and it's blowing north, north, and east. Anybody have an idea what the angle would be there? Yeah, it's a 45-degree angle. That's why I picked north and east. And I wouldn't pick anything harder than that for this kind of problem, because then it's a little bit too much work. All right, let's make that, say, a different color, and we'll thicker. Okay. That's the jet stream. So is the wind helping the plane, or is it going to slow the plane down? Yeah, it's not like the plane's trying to fly directly into the wind, but the jet stream is trying to blow north and east. The plane is trying to go south. Okay, so what's going to happen if we want to see where the plane is really going to end up? We could do what we learned the first day. Combine the two vectors together. The one for the plane, the one for the wind. So the plane is going to really end up going that way if the pilot doesn't adjust his direction. He's going to be blown off course to the east, and he's going to be slowed down a little bit by the wind. Okay, so I just put that in so you could kind of see the black line. That's going to be where plane is blown to. Blown off course. Right, so our goal is basically to figure out what is that vector. How do we represent that black vector in numbers? Well, let's start by representing the original ones with numbers. Let's start with the plane. So I'm going to represent it as I and j. What's the horizontal component of the plane? How far left and right is that red vector going? 0. The plane is flying straight down. There's only a vertical component to the vector in red. Okay, so no horizontal. What about the vertical? What was the speed of the plane? 500j, and it's south. So how would we represent that? Negative 500j. That's a vector that represents the plane. Negative 500 down, j. All right. Now let's figure out a vector for the jet stream. Okay, this one's at an angle. So it's going to be whatever amount horizontal and vertical, they're the same, okay, because it's a 45-degree angle. So your horizontal and vertical components are the same, but we need to figure out what are those two components. So what we'll do is we'll use the velocity vector from yesterday. That way, that'll help us figure it out without having to come up with a new formula. This is going to be the formula we fill in. So cosine. First, let's start with the velocity. How fast is the jet stream? Yep, 80. And what's the angle the jet stream is blowing at?
45.
It's a 45-degree angle. Okay, let's do that out, and then we're going to get another vector. Then we'll have both the vectors we need. So take cosine 45 times 80. 56.6i. And now j has to be the same, because it's blowing at a 45-degree angle, but if you're not sure, do it out. Sine of 45 times 80, 56.6 again. Question on how we represented the wind as a vector, or the speed of the plane as a vector. Now just combine the two together. And that's your new vector. Now we're not going to combine them by doing that. That's the old way where we do it visually. We put it's called head to tail, connect the beginning to the end. We're just going to add the numbers up. All right, so we've got negative 500j plus this vector. Okay, so let's just write them a little closer. So that one plus the other one. I put the 0 in there in case some people get confused if they don't see something for I. It's 0. It's nothing for the plane. What do you get when you add up your I components there? How much? 56.6 I. And the j components, it's negative 500 plus 56.6. So the plane is still heading south, but it's only heading south at 443 miles an hour. So the instruments would say he's going 500, but really, he's only going 443 miles an hour. So, what was it? 443.4. So that's the vector for the plane being blown off course. Any question on that? All right, so the last thing I'll do, I'm not going to find the angle, but I will find the speed. So if somebody was looking at this plane on the ground, how fast would it look like the plane is going? Well, the plane is going 56.6 miles per hour east. So for every hour that goes by, the plane is 56 more miles east than it should be. And then it's also 443 miles per hour south. South is good. That's where the pilot wants to go. But he doesn't want to be going east. So he'd have to correct for that. All right, let's find the speed on the ground. So the plane's heading, that's the 443, south, and it's also heading east. I'm just trying to help you visualize south and east. And that's a 90-degree angle. Okay, well, you know what? If it makes more sense, you can put it there too. Same thing. So how would you find that? You want to find what the speed of the plane really is. This side is 56.6. The height here is 443.4, and I want to know the hypotenuse. That's the direction the plane is traveling in. Think of it as just finding the length of a side in a triangle. You don't even need anything that I've shown you. The side of the triangle is 56.6. That side is 443.4. How would you find the length of the third side? Yeah, it's the Pythagorean theorem. That will give you the length of the third side of the triangle. Okay? If you think of everything in terms of a triangle rather than thinking about the word problem, that's a lot easier. Okay, so let's find the length of the side of the triangle. So it's 43.4 squared plus 56.6 squared. And call the hypotenuse whatever you want, x. Right, so let's see what we get for the speed of the plane. So 443.4 squared plus 56.6 squared. Add them up. And what's the last thing I need to do with that number? Take the square root. So the speed of the plane is about 447 miles per hour. So if somebody was looking at that plane from the ground, that's how fast it would look like it's going. Even though the pilot would think he's going 500 miles an hour, the wind is going to change that. Okay, any question on that? So again, main idea, I make a sketch, try to represent each vector on that diagram. Write the numbers out for each vector, and then we just combined them, got a new vector, and that's basically it. Okay, we use the Pythagorean theorem to finish it off. Okay, but that's the only application we'll do for dot product. Okay, and actually, I avoided dot product here. The way I avoided it is I didn't end up finding that angle. They also asked me to find what's the angle the pilot's being blown off course. I skipped over that. You don't have to worry about that either. Just his speed. All right, so for tonight, the homework on 352. Okay, I'd like you to try it 7 to 17, just the odds. Each question has 3 parts. They ask you to find the dot product, find the angle, which you have to find the dot product anyway. And then once you find the angle, they ask you, are the vectors parallel, perpendicular, or neither? Okay. And then also try 25. Okay, that's an airplane one. So if you get stuck on it, we'll try it together tomorrow.